Hello students, we are dealing with unit 4, that is partial differential equations and their applications from our M3 syllabus. So far we have seen the definition of partial differential equation, its order and degree. Also we have seen how to form the partial differential equation by eliminating the arbitrary constants in the given function z. Now we are going to see how to form partial differential equation by eliminating arbitrary functions in the given function z. Definition of partial differential equation we have seen. It is very similar to the definition of differential equation. It is nothing but the differential equation containing the partial derivatives first order, second order with respect to x, y as per the given function. The order of the partial differential equation is nothing but the order of the highest order derivative present in the given equation and the degree of the highest order derivative present in the given partial differential equation, which is free from radical sign and fractional powers, is called as degree of the given partial differential equation. Also we have seen that partial differential equation can be formed in two ways. First, by eliminating arbitrary constant, and the second way is by eliminating arbitrary functions. For this we are using some notations. If z equal to f of xy, then the first order partial derivatives of z with respect to x and y are denoted by p and q respectively, and the second order partial derivatives of z with respect to x, xy and y are denoted by r, s and t respectively. Now we will see the formation of PDE by eliminating the arbitrary function. So question will be like this: form the PDE by eliminating the arbitrary function from the following. First example, z equal to f of x square minus y square. In this function, f is a arbitrary function and we have to eliminate it. Obviously, we have to form the partial differential equation. So we have to take the partial derivative of this given function z with respect to x and with respect to y. Here z is a dependent variable and x and y are independent variables. So let us see the solution. First step, write the given function as it is, call it as equation 1. Now differentiating this equation 1 partially with respect to x, we get partially with respect to x means all the terms which are containing independent variable y should be treated as a constant. So differentiating this equation 1 partially with respect to x, we get dou z by dou x is LHS equal to f dash of x square minus y square, and derivative of x square minus y square partially with respect to x is 2x. Now dou z by dou x is replaced by p and RHS is written as 2x into f dash of x square minus y square. Similarly, differentiating equation 1 partially with respect to y, we get q equal to minus 2y f dash of x square minus y square. So now in equation 2 and equation 3 we are having f dash. We can remove this f dash to form the partial differential equation, which is the required thing. So by multiplying equation 2 by y and equation 3 by x and adding the resultant equations, we get py plus qx equal to 2xy f dash of x square minus y square minus 2xy f dash of x square minus y square. So it clearly indicates that RHS is 0. So we get the equation as py plus qx equal to 0. So this is the required partial differential equation, which is obtained by eliminating the arbitrary function small f from the given function z. we will see one more example. Here f of xy plus z square and x plus y plus z equal to 0 is the given function. Again here the arbitrary function used is function f. Z is dependent variable and x and y are independent variables. We have to eliminate f to form the partial differential equation. So let us see the solution. Here the function f is of two complicated functions, so we can call them as u and v. Let u equal to xy plus z square and v equal to x plus y plus z. So the given function becomes simple one, that is f of u v equal to 0. Let us call this equation as equation 1. Now we can represent all this function of u and v, which are again functions of x and y and z, in a diagrammatic form. So f is function of u and v, u is function of x, y, z, v is function of x, y, z, and again z is function of x and y. So using this diagram, we can write the partial derivatives very easily applying the chain rule. So differentiating equation 1 partially with respect to x by chain rule and referring this diagram, we get dou f by dou u into bracket dou u by dou x plus dou u by dou z into dou z by dou x. Again you can reach from f to x through v also. So plus dou f by dou v into bracket dou v by dou x plus dou v by dou z into dou z by dou x. Now you are having function u with u and function v with u. You can find dou u by dou x, dou v by dou x. Also you can find dou u by dou z and dou v by dou z. So from these two functions we can find these four partial derivatives, and using these results we can write dou f by dou u into y plus 2 zp plus dou f by dou v into 1 plus 1 into p. Here function f is a function of u and v, but it is not mentioned particularly. So we cannot find dou f by dou u and dou f by dou v in particular. So simplifying, we get dou f by dou u equal to dou f by dou u into y plus 2 zp plus dou f by dou v into 1 plus p equal to 0. This is your result 2. Now result 2 is containing dou f by dou u, dou f by dou v, y, p, z. But out of these terms we don't want dou f by dou u and dou f by dou v. Means we have to eliminate these two terms. So if we can have one more equation containing dou f by dou u and dou f by dou v, we can apply the method of solving the simultaneous linear equations to eliminate any one of these two unknowns. So let us move to the next part. So differentiating this equation 1 partially with respect to y and applying chain rule, we get the term as dou f by dou u into dou u by dou y plus dou u by dou z into dou z by dou y. Again dou f by dou v into dou v by dou y plus dou v by dou z into dou z by dou y and equal to 0, as the RHS is 0. Again using the particular results for dou u by dou y, dou u by dou z, dou v by dou y and dou v by dou z, by the definitions of u and v function, we can write dou f by dou u into bracket x plus 2zq plus dou f by dou v into bracket 1 plus 1 into q. Simplifying this, we get dou f by dou u into x plus 2zq plus dou f by dou v into 1 plus q equal to 0. So result 2 and result 3 are the simultaneous linear equations in two unknowns, dou f by dou u and dou f by dou v. So we can eliminate them by making one of these terms coefficients equal with some multiplication. So multiplying equation 2 by 1 plus q and equation 3 by 1 plus p and subtracting the obtained results, we get this equation. You may observe here the second term and the last term get cancelled as they are having opposite sign. So we get dou f by dou u into y plus 2zp into 1 plus q minus dou f by dou u into x plus 2zq into 1 plus p. So here we can shift this second term to RHS and we can cancel this dou f by dou u factor from both sides, so that we can have the equation containing only x, y, z, p and q, and here we are not having any f or its partial derivative term. So in this way we have eliminated the function, arbitrary function f from the given function. But we have to rearrange the terms so as to get the PDE in proper form. So just by multiplying by term by term we get this step. Then here also this 2zpq and 2zpq is present with same sign on both the sides of the equal to sign. So we can eliminate the term and then we can collect the terms containing p and q on LHS and the terms without p and q on RHS. Then by taking p common from first two terms and by taking q common from last two terms, we can write the equation as p into 2z minus x plus q into y minus 2z equal to x minus y. And this is the required partial differential equation which is obtained by eliminating the arbitrary function f from the given function z. Referring these two solutions, you can solve examples to form the PDE. So these are the three examples and you can verify their answers from your M3 book by Dr. B.B. Singh sir. So thank you very much for listening patiently.